Okay, now?
Yeah, you're back. You're back.
And you see the Grasshopper window, right?
Yes, yes.
Okay. Okay, hey again to those who have been here in the morning. This is very short workshop, very short tutorial, and I'd like to use this opportunity to show the process which we're using in our studio. And I'd like to show it on a particular project. So currently we're working on a project for Linz, for the Ars Electronica Festival. I don't know if I should have said that. Anyways, the project is concerned with public space, creating some sort of artificial landscape, which somehow reflects on this current post-COVID, post-coronavirus situation. Everybody knows about social spacing, and the general idea is that the landscape would kind of enforce, or not enforce is a strong word, but kind of manipulate people into arrange themselves more loosely in the public space. Here just a sketch, so to give you an idea what we are working on, just a very initial sketch of this kind of landscape. The idea is to create uneven surface, which is totally possible. If you want to pass through, you can just, as you see, the unevenness is relatively small. It's like 5-6 centimeters, so you can go through. Even if you're handicapped, you can the wheelchair can go through. However, if you just stay there, hang out there, naturally you would prefer to stay on a flat bit of landscape rather than on a curvy one, which is lower. So the idea, this initial sketch is supposed to show you that the idea is that would kind of space people out. Also, we want to kind of slow down the movement and create some sort of erosion pattern, which would work partly as a drainage. For all those reasons, for the reasons of creating some sort of spacing and some sort of slowing down of the movement, we thought to use one particular algorithm, and that is an algorithm of generative growth. You might have known this algorithm from such natural phenomena as corals or some plants, or even some cells in organisms like brain cells, etc., etc. Generally, the idea behind it is that some cells grow faster than the others, and that creates quite complex and quite sophisticated topologies. Just to give you an idea, stuff which looks like that. It also is related within the field of structural design to the phenomenon of buckling, because buckling essentially is when a structure collapses with different bits of structure collapse with different speed, or bend with deform with different speed. So it's not a coincidence that these things look similar. Anyway, this is a sort of abstract phenomenon. This is a practical application, and today I'm going to talk about the abstract bit. For this tutorial, we're going to use Rhino. We're going to use Grasshopper, which is basically a visual scripting platform within Rhino, and we're going to use a couple of plugins. Well, it would be impossible, obviously, to create something at least a little bit interesting in a way that the tutorial would be aimed on complete beginners, and to do that in half an hour. Still, if you have never used Grasshopper before and you would go through this video, you should be able to repeat what I'm doing and maybe then change something. However, obviously, it's not your typical starting video. It's not like maybe it's not greatest video to like start learning Grasshopper from the beginning. You would be able to repeat it, but I would not explain the basics within this video. Besides Grasshopper, we are going to use a couple of plugins. One plugin, probably I should start. We're going to use a plugin called Kangaroo 2, which is physics simulation plugin. However, if you have Rhino 6, Kangaroo 2 is already installed within Grasshopper for Rhino 6. If you have Rhino 5, you would have to install a plugin called Kangaroo 2. Other plugin which we're going to use is Anemone. I believe it's not installed in Rhino 6. Anyway, for all those plugins, you can look for the website called foodforrhino.com, and the plugins could be downloaded for free from there. You just, you type the name of the plugin. So I'm going to type Anemone. That's the one. And you would need to download the latest version, in this case, Anemone 0.4.
Shota, I think that you're only sharing the Rhino window, so we only see the Rhino still.
All right, okay. Then...
But I think I was already showing Anemone in one of my previous workshops, so maybe.
All right, then I'll stay
of...
there.
Yeah.
I'll stay in Rhino.
Yeah.
Basically, maybe I'll just show.
Just show the list of plugins that you're using, and I think that will be.
Oh yeah, then I'll say it.
Yeah.
So Kangaroo 2, I'm using it. Anemone, I'm using it, and Weaverbird. Weaverbird is a little bit different because it's not this typical Grasshopper plugin which you copy in the special folders, component folders. It's also for Rhino, but it's also pretty straightforward to install. You just and it's not on Food for Rhino. You just type. It's on Giulia Piacentino's website. You just type Weaverbird, Google it, and you'll figure it out. As we agreed with Jan, I'm not gonna now go through installation process. I'll just carry on, and later you can go through this video, stop it, and if it's okay. All right. So yeah, as I said, maybe these three plugins, Anemone, Kangaroo, and Weaverbird. Maybe just short mention why I need those. Anemone is a plugin which helps to do iterative stuff. Generally, iterative processes, iterative algorithms, when you repeat something many times, is essential part of any scripting. However, within Grasshopper, it's quite funny. All kinds of iterations are only possible within components. So within this, these buttons which you have here, their iterations are going on. However, if you create a chunk of code from several components, normally Grasshopper would not allow you to iterate, would not allow you to create closed loop. So several plugins were created. As far as I know, Anemone is the most successful one. There was an unfortunate thing called Hoopsnake some years ago, but I would suggest using it. Since differential growth processes is basically, as any growth process is something repetitive, we would gonna use that. Then plugin Kangaroo 2 is physics simulation plugin. It simulates, it's generally a spring engine. It kind of substitutes all the connections with this imaginary springs, which simulate different forces, attraction forces, repelling forces, etc. From simple spring engine, it evolved to quite complex thing, where you can do quite complex simulations, really fancy stuff. Still, it's quite easy, and it's very stable. Especially the second version, Kangaroo 2, has improved its stability. So all the kind of physics simulations which are part of the growth, so the fact that the geometries would not grow through each other, and this kind of things, or the growth itself has been done in Kangaroo, will be done in Kangaroo 2. And finally, Weaverbird is a plugin which deals with meshes, with particularly subdividing meshes, some useful tool. It's not essential for this particular script, but this particular script is much simpler using Weaverbird, so I'm going to show it. Now, before I actually start scripting, maybe I'll try to explain you the concept of differential growth. So the idea, as it comes from the name, is the fact that some cells grow faster than the others, and that leads to a deformation of form, deformation of the growing element. You can imagine this very simple matrix of let's say something like that. And imagine that each of those lines increase in size. If they increase all in size equally, then eventually this thing would just become bigger. And no deformation happens. However, if let's say that we say that this line, this one, grows faster than all the others, then what we will have very soon would be something like that. You see this little curvature which has appeared because this line grew faster is basically a driver for all kinds of differential growth processes. Of course, the geometries we are talking about are much more complex. So this has 10 elements or something like that, and we're going to work with meshes which would have hundreds or thousands of elements, and hence the growth ends up we end up with much more complex results as you see here. This is a little bit simplified explanation of the phenomenon of the differential growth. What we're going to do is actually a little bit different. Instead of starting with a bunch of exactly same elements like those lines, and then letting one of them become bigger than the others, we will do the opposite. We'll start with a bunch of elements. Each of them are different in size, and we will make the physics simulation plugin Kangaroo. We'll try to make them the same size. However, the result of this transformation is the same. Since different elements become the same, that means then they grow or they change in size differently, hence differential growth, hence curvy complex topologies as you see here. I think that's all a theoretical explanation I'm going to give. Generally, if you want to look into differential growth, there are plenty of articles and some very beautiful projects. I particularly suggest work of designers called Nervous Systems. I think the website is nervous.com, and you have a dash between each letter, so N-E-R, etc. Differential growth was a big part of their process, their creative process.
Also, so there is a very nice paper on this by Andy Lomas. He made a series of videos where he's simulating similar things in real time. I will post a link to the paper to the chat. But you can actually read about the mathematics behind.
Yeah, great. We previously were dealing with our students with differential growth in case of 1D elements, so like lines or curves, which is a bit simpler. And generally, whenever I encountered different scripts on the internet which apply differential growth on 2D elements, so surfaces or meshes, they were often using custom-made scripted components, which make them faster, which is nice, but which I also found being a little bit of a boundary for the beginners who maybe know Grasshopper, but they don't know C# or Python. So one of ideas behind this project for me also was to create a script which I can share with people who start. Okay, I'm going to start now. I'm going to start with creating a very simple mesh. So here in mesh, in primitives, you can find this construct mesh component. Let me see if I'm going to hide these things. Okay, here am I. Oh, actually, I can, yeah, let's make it a little bit faster. I will directly create a mesh plane. here you can put a boundary, which I'm not putting, and here you can change the number of faces, which I'm not doing as well. It's 10 by 10. Later you can change it. Basically, at this point doesn't matter. Something which I have encountered previously is that somehow Kangaroo limits itself. Maybe Ján would know this. Kangaroo limits itself to 2D if you put the 2D elements. So differential growth kind of doesn't start unless you kind of get out of this XY plane. So first thing I'm gonna do is I'm gonna.
I don't think it's really limiting itself, but I think there is no force that would push the elements vertically. Like all the forces have all the force vectors have a zero z component, and therefore there is no pressure on the component to change.
Maybe. Anyways,
yeah, I'm pretty sure it's the case.
Just rotating stuff out of a plane without adding anything else helps. So I'm gonna use some of the many rotate. That was a mystery for me why Grasshopper has so many rotate components, but yeah, it does. So for example, this one, I'm gonna rotate this in let's say XZ plane by let's say 0.1 radians. So, you know, now it's not flat and it will work. I'm gonna hide the first one so it doesn't confuse me. I'm gonna work with triangulated mesh. I think it's also not an essential thing. However, I wanted the script initially to be kind of generic. So I'm not only using this mesh, but also some meshes which I import. And mostly you have triangulated meshes unless they are somehow regular. So I'm triangulating it now. Later you can try on your own. Now I'm going to do the thing which later would be repeated many times. So I'll just type it right now or create it right now. However, maybe I can put this line here so we know that from here on we will insert the anemone component. But it would be something which will be repeated. So I have a mesh here. Just to make it more visible, I'm going to create mesh container, which is triangulated and which is slightly tilted, and that's pretty much it. I'm gonna now put one of the Weaverbird subdivision algorithms here. I'm gonna use Catmull-Clark subdivision. The reason for that is it would immediately create a mesh which has phases which are slightly irregular. This tiny irregularity, some of them are smaller, some of them are bigger, the phase edges, is already enough to start up the differential growth process. So here is my slightly irregular mesh, and I'm gonna create forces which later I'm gonna use in Kangaroo. One, I would need to make sure that mesh doesn't collide with itself, so that it doesn't grow through itself. Kangaroo 2 has a very nice component called sphere collide. Basically, it creates this imaginary sphere around each point, and this sphere doesn't collide with another spheres, and it's very fast. It's a very nice component. However, what you need to put inside this points input is all the vertices of the mesh. So I'm gonna create those. Deconstruct mesh, or what is it? Deconstruct mesh. I'm pretty sure it's not the case, but just to be on the safe side, I'm gonna use remove duplicate points, which should make sure if there are several points they're duplicating, it would get rid of them. So we have our spheres. Another component, just to still have our mesh, so it doesn't, you know, fly away, because the sphere collide makes sure points are not too close to each other, but we also need to make sure they are not too far away of each other. Is a very basic goal. It's called length line, which basically makes sure that the edges of the mesh would not be infinitely stretchable. So again, I take this mesh, I use mesh edges component, mesh edges here, and the outer edges, naked edges of the mesh, these are those, and the inner edges, these are those, E2, they all go here. I'm not gonna put anything in the length, and that would ensure that the lengths would try to stay the same. Maybe one more thing with sphere collide. Basically, I need the spheres to be bigger than the half distance between the meshes, so it actually grows. I think my mesh is 10 by 10 and 10 by 10 faces, and the 20 by 20 units, millimeters, or whatever I'm using. So one face is 2 units long, so half the distance is 1 unit long. Actually, here the faces are even smaller. I'm just going to type 1.5 or 1.7. Later we can change this value. That would ensure that the spheres would not fit there by themselves. They would try to expand the size of this mesh, expand the growth. Normally within this physics simulation, you would use normal kangaroo solver. However, kangaroo solver runs indefinitely until you either stop it or until it finds such an equilibrium that nothing changes, nothing happens. Because we're gonna iterate this, we're gonna run this many, many times. I don't want my solver to run indefinitely, so I'm gonna use zombie solver, which basically is a kangaroo solver where you put the amount of iterations you want it to run and it just shows you the result. So stuff you put in the goal objects is this and this. I should have put the number of iterations, because I guess the default value is quite big. So I'm gonna wait a little bit. Yeah, so the default value is 50,000. I'll be fine. And you see what it does. It already did some kind of deformation at 50,000, but 50,000 is way too much. So I'm gonna put 50. Much less deformation, if any, almost nothing. But it's fine. When we would run it many, many times, it will work out. What you see here is the result of this simulation is not a mesh, it's just a bunch of lines, because that's what we put in. We put in edges and we put in points. If you want to see a mesh, you need one more goal, that is show. Show is a goal which doesn't do anything. It just makes sure that the stuff you want to see is there in the result. So I'm going to connect the mesh here to the show component, and I'm going to connect the show component here to the goal objects. The mesh here is the first of the outputs, so I'm going to use list item to get a mesh. So basically here we have a process, and I'm going to draw one more line here. Here we have a process from this point to this point, which would be repeated many, many times. So let's go into the repetition. I'm going to create an simple anemone loop. Unlike fast loop, this one shows us what's going on, which is nice. The fast loop would do exactly the same thing, but it would just show you the final result. For now, I'm gonna say that the number of repeats is 0, because, well, you never know what goes wrong. So the mesh goes here, goes through the loop, comes back here. This thing's happening, and it goes back here. And to close the loop, we connect the back directed arrow to the forward directed arrow. So we have the loop here. And it theoretically should run indefinitely. The problem with this script as it is now, I'm not even gonna, well, I can try just 3 repetitions, for example, or 2 repetitions. Well, you already see the problem with this script is that at any repetition, well, you have quite nice growth structure here, I quite like it, but at any repetition, this component exponentially increases the number of faces, because this Catmull-Clark subdivision creates 3 more faces of any triangle. So if initially we had mesh which had 200 faces, after the first loop it had 600, then it had 1,800, etc., etc., etc. So after 3 repetitions, 0, 1, 2, 3 repetitions, we're already at how many? 9,600 faces. That's why it took a little bit of time. Obviously, the solver particularly is most time consuming. And if I would put 10 repetitions, I'm pretty sure it would freeze my computer and it would never finish. So I'm gonna change the script a little bit. Everything which is going on, I quite like. However, this subdivision would only happen every X number of steps, let's say 10, for example. So first it subdivides it. Then it just runs the zombie component several times, allows for the growth. And then after 10 steps, it subdivides it again. How to implement it? That's pretty simple. We have counter here. We create a component called modulus. Modulus is an arithmetic function which gives you a remainder of division. So you divide it by 10. And the remainder, if it is 0, remainder is 0. If it is 1, it's 1, up to 10. If it's 10, it's again 0, 11 is 1, etc., etc. And we check if the remainder is equal to 0. So it is only equal to 0 every 10 steps. I guess there are actually other ways to do it. I'm sure there are other ways to do it. This just happened to be in my mind when I tried the script. The result here is either true or false, either remainder is 0 or it isn't. And I'm going to use dispatch component, which basically, depending on whether it's true or false, would dispatch stuff into A output or into B output. So mesh would go here. The pattern, true or false, goes here. So right now it's false, so there is nothing in A, but everything is here in B. So whenever it is true, whenever stuff is in A, I'm going to do the subdivision. So Catmull-Clark goes here. However, whenever it's not, this thing B would go to the kangaroo simulation directly. So I'm going to need one more component here. Doesn't really matter what to put there. We can put clean tree and flatten the input. So this all outputs would go out of clean tree. Catmull-Clark would grow here, and B would grow here as well. So that should do it. So now I'm gonna move this a little bit so it's more visual. Now this little loop, this bit, what you see here, only happens every 10 steps. Otherwise, it goes directly and does this thing directly. So I'm going to run this again. If you double click the loop start, it would rerun it. You see it's much faster because it only did the subdivision once and it hasn't done it since. So I'm going to do, let's say, 16 iterations. It runs, it grows, it doesn't subdivide again. Now there was a jump because it has subdivided it again and it grows again. So I managed to do more iterations without subdivision. Yeah, here is some resulting shape. If you want the shape more smooth, you can add Catmull-Clark subdivision again after the loop, there it would not affect anything, just the resulting shape. So it's a bit smoother, and I can hide everything except the end result. So yeah, here basically you have the process. I think this is fast enough, so I'm gonna increase the number here. Let's say 22 steps. So it continues growing already quite slowly. Now it's, I guess, 20th step. So there is a jump. Grasshopper has disappeared, but I'm pretty sure it will be back. Yeah, it's back. Yeah, it's here. So here we have the result, just out of curiosity, 38,000 faces, so already quite big. But as you see, it's quite nicely packed. There is no self-intersection, nothing like that. And quite nice topology. You can bake the results and look into them in Rhino, for example, in the rendered view, or use clipping plane to see what is it like in section, like this. That's it. That's what I wanted to show today. So if there are any questions, I'll answer it. Otherwise, I guess I will send this to Janu, so Janu can publish the script.